Hi everybody. Today we're going to be talking about sequences. Alright, so this is where we're going to start chapter 11 in our book. And chapter 11 in our book is going to talk about sequences and series. And so the first section that we talk about is then sequences. Now, let's start off by defining what a sequence is. So we have here on screen that a sequence, and then we give the notation that a sub n, we typically use these squiggly braces here to denote that we have a sequence. And this is going to be an ordered list of numbers of the form a sub 1, a sub 2, a sub 3, a sub 4, so on and so forth, all the way to some stopping point. Alright, now I also have this arrow drawn here from that sequence, that when we have a sequence, we can have two types of different sequences. One sequence will be an infinite sequence where we're looking at the sequence given by some random function. The integer value will begin at 1, and then the series will then just tailor off into infinity. Alright? Or we can have a finite sequence. A finite sequence means that this sequence will have a stopping point. And so here I gave you two quick, brief views into what an infinite sequence looks like and what a finite sequence looks like. Alright, again, the only difference is where the stopping point is at. Now, we can also have a sequence defined by a recurrence relation. This means that your recurrence relation or your sequence is based off of a previous term or some previous terms. Alright, one of the most famous sequences that we can talk about for a recurrence relation would be the Fibonacci sequence. Alright, the Fibonacci sequence is a sequence that's built upon previous numbers. So it typically starts with 1, and then it's another 1, and then we do 1 plus 1, which gets us 2. Then the rest of the sequence is just defined by adding the two previous terms together. So we would get 3 as the next term, then add 2 and 3, we'd get 5, then add 5 and 3, then we'd get 8, 8 and 5, then we'd get 13, 13 and 8, that would then get us 21, so on and so forth. Alright, again, this is known as your Fibonacci sequence. And it's a very important, very interesting sequence that we like to look at in math. There's a lot of discoveries that have been made in the past few years, and more discoveries are being made about this Fibonacci sequence and how it pertains to probability, which is really, really interesting. All right. Now, the third part of the definition says that a sequence may also be defined by an explicit formula. Alright, so explicit formula, what they mean is this particular piece right here. So if you notice the examples that I gave you for the infinite and the finite sequences here, for these particular examples, the formula that is defined is known as an explicit formula, meaning that we can use variables to describe what is this function going to produce for the next numerical value. Alright, kind of like creating a function, and that's exactly how we work with it. We say that if we have a sequence that can be generated with an explicit formula, we're typically going to denote it a sub n. But a sub n just basically translates into a function that has a variable n that we're going to be observing. Alright, so that's how we typically like to work with sequences. Alright, so now that we have this whole idea and this whole process for how to work with sequences, let's now start looking at how do we find these terms and how do we generate these sequences. So, if you look at this example, we're going to do two examples here, part A and part B, and the instructions are going to say to calculate the first 4 terms of the sequence. Alright, so again, we want to calculate the first 4 terms. So what that means for us, first 4 terms, means that we're going to have to find n is equal to 1, 2, 3, and 4 in accordance to our formulas right up here. Alright, so let's start generating some of those values. So if we take n is equal to 1, n is equal to 1, here for the very first formula, we're going to get that n is equal to 1. That's going to be c sub 1 is going to be 3 to the power of 1 divided by 1 factorial. Now, 3 to the power of 1, that's just 3. 1 factorial, that's just 1, which means this answer is just 3. N is equal to 2. All right, that's going to be c sub 2. This is going to be 3 to the power of n, where n is 2, divided by n factorial, which in our case is 2 factorial. This naturally becomes numerator is 9, denominator is 2. There we are. N is equal to 3. N is equal to 3, that's going to be our c sub 3 term, which means this is going to be 3 to the power of 3 divided by 3 factorial. Alright, now I'm not going to expand here. Instead, I'm just going to write it in exponential notation or multiplication notation, product notation here. So we're then able to see that the leading 3's then cancel or simplify here, and we're just left with 9/2 once again. And then finally we have the very last term, which is going to be n is equal to 4, and that's going to be our c sub 4. This is going to be 3 to the power of 4 divided by 4 factorial. So again, 3 to the power of 4, 3 times 3 times 3 times 3, divided by 4 times 3 times 2 times 1 because of that factorial. And now here we get to see that one of the 3's in the numerator and the denominator will cancel out individually. And then we will be left with here 3 times 3 times 3. That should get us here 27. And then 4 times 2, that should get us 8. So the answer here should be 27 divided by 8. All right. Now, this is nice. All right. What I'm going to do really quickly is, now that I've generated these terms, what I'm going to do is I'm going to list them out in sequence notation. That way, whoever's reading this or whoever's observing this can automatically extract this is what this sequence is generating. All right. So let's look at this. Sequence notation, 3 to the power of n divided by n factorial. My index here starts at n is equal to 1, and I generated the first 4 terms, which means I'm stopping at the number 4. Right, just like this. The sequence that was generated is the list of numbers. 3, 9/2, 9/2, and then 27 over 8. And again, if you observe this, well then the first one was c sub 1, the second one was c sub 2, the third one was c sub 3, and the last one was c sub 4, where we initially had our c sub n formula. Right, so at the end of the day, this is what I want to see. I want to see that list of numbers being generated, and that is the sequence. Alright, so I'm going to take a quick detour really quick, and I'm going to show you a visualization of what it is that we're doing here. Alright, so please follow me along really quick, and we're going to go on to Geogebra. Here I am with my old friend Geogebra. Alright, so what I have here on the left hand side is I created this applet in order for this to generate some of these terms that we're going to be looking at for our sequence. The formula that I input here is the same formula that we saw in the previous example, which was the sequence defined by 3 to the power of n divided by n factorial. So at this point in time, what I'm going to do is I'm going to start sliding these points in order to generate these values. All right, now really quickly, you're going to notice that I programmed this to start at n is equal to 0. Typically we want to have our indices always start at 1, but they can technically start at anywhere we'd like. So here we go. Start generating some of these points. There we are. So you should see the points populate here on screen. Alright, now I'm going to omit the first one because the first one is where n is equal to 0. If n is equal to 0, then 3 to the power of 0 is going to be 1 divided by 0 factorial, but 0 factorial is just 1, so it really just becomes 1 divided by 1, and you see here the y value, or the output, is just 1. So again, if we start looking at this relation here as an explicit formula, then that explicit formula is really just a function that is being modeled. So let's see if we can generate the numbers that we were looking at. When n is equal to 1, in other words, this formula here is going to be input for a 1 value. So in our x-coordinate, x is 1, our output was 3. It gets us the exact same output that we were observing. So 3 is the first number that we look at. That was c sub 1. c sub 2, integer value of 2. The output here is 4.5. Now, another name for 4.5, or an equivalent form of 4.5, is 9 divided by 2. Well, what about x is equal to 3? 9 over 2, once again, that 4.5. Third one gets us 4. C sub 4 gets us, in this particular case, we're going to be looking at c sub 4 is going to be 27 divided by 8. Now, when we do 27 divided by 8, it gets us 3.375. So 3.375, and if you're going to notice, it's plotted right there. So if we go to 5, then we'd get an answer similar to that. 6, we'd get an answer similar to 1, and then 7, so on and so forth, 8, so on and so forth. All right, now, let's try to forecast ahead a little bit. I want you to look at this function here, or at least this sequence of numbers. This sequence of numbers kind of creates this graph-looking feature. And that's kind of what we want to go into, because according to the calculus work that we've done before, right, we know how to perform calculus on these functions, but what if we could model functions with sequences of numbers? Then that just adds this whole new level of looking at these functions that we thought about back in calculus, back in Calc 1, beginning part of Calc 2. All right, so without getting too far into that theory, this is what we want to see. All right, awesome. So follow me back to the whiteboard. All right, so here we are. Now, I want to go ahead and I want to generate the rest of these numbers here for this cosine of n pi divided by 2. So once again, I'm going to go through and I'm going to generate the first 4 terms. So this is going to be n is equal to 1, n is equal to 2, n is equal to 3, and then n is equal to 4. So for the first one, this is going to be a sub 1. All right, they're giving me my sequence formula. Here's a sub n, so a sub 1. This is going to be cosine of n is 1, so this is just going to be pi halves. So cosine evaluated at pi halves, this should get us 0. A sub 2 is going to be cosine at 2 pi divided by 2. That's just going to be pi. Cosine at pi is negative 1. A sub 3, this is going to be cosine at 3 pi halves. Cosine at 3 pi halves, that should get us 0. And then finally, a sub 4, this is going to be cosine at 4 pi divided by 2, in other words, 2 pi. So cosine at 2 pi should just get us a 1. Now, what does this sequence look like when we put it into notation form? Well, this is going to be cosine of n pi over 2. Oops. There we are. We're going to start at n is equal to 1, and we're going to go all the way to 4, which means the sequence of numbers that we're generating here is 0, negative 1, 0, and 1. Just like that. So let's go back and let's look at this series on GeoGebra, this sequence on GeoGebra, and see what is taking place within that sequence. All right, so here we are. So I typed in the function here, the function being cosine of x times pi divided by 2. The variable that I'm using is x here for GeoGebra, but for the class example I used n, which again at the end of the day it shouldn't make a difference what the variable is. Typically we like to use n, but at the end of the day it does not matter. All right, so I want you to look at that sequence. All right, that sequence goes from here, it goes from 0, -1 to 0 to 1 to 0, back down to -1. And it just keeps alternating between those three values. So as we tend to go off towards infinity, so as these values go off towards infinity, all we're doing is just alternating between 0, 1, and -1. Now that's going to be an important concept, that if this sequence tends to infinity, what is the overall tail of this sequence doing? In other words, what is the end behavior of the sequence? That is something that we are going to have to evaluate, just not at this time. All right, so keep that in your back pocket or in the back of your minds and we'll get to it. All right, so let's go back and let's try different examples. All right, here we are. So what I want to do now is I want to go into this example here where we are going to have to find a formula for the general term a sub n of this sequence. All right, so what I'm looking at by definition up here, I'm looking for an explicit formula. All right, I'm not looking for a recurrence relation, I'm looking for an explicit formula. In other words, whatever formula I find, I hope or my wish is that that formula does not depend on any previous term to be added to it. All right, so in other words, what we're going to have to do is we're going to have to start analyzing patterns. All right, so in this particular case, we want to analyze patterns to establish a formula. So we're going to have to try to analyze what patterns are occurring here. Now, one of the first things that you're going to notice here, and I'm going to write these noticeable things here in orange. One thing that's noticeable is that this negative is kind of alternating, right? This negative skips one term and then the next term becomes negative, skips a term in the middle, next term is negative, skips it, and then the next one is going to be negative. So we get an alternating sequence, which means we're going to have a negative value in there somewhere. Now, the big item, the big takeaway from an alternating sequence is this, that when I have an alternating sequence, I'm going to have this -1 to some power n. Because as we like to look at this, well, if n is 1, then that means this is going to be negative. If n is 2, then that means this is positive. If n is 3, that's negative. If n is 4, that means it's positive. So that value will then keep alternating between negative, positive, negative, positive. And we want to have that at our disposal. Now, the second thing that we're going to notice, now I want you to strip away those negative values. So ignoring those negative values, let's just analyze the numerical components. 1, 2, 3, 4, 5. This is just increasing by 1. And I'm going to put increasing in quotations because, again, it's not technically increasing unless you're stripping away the negative signs. So increasing by 1. All right. This to me tells me that my overall function should just be n. Because if it's increasing by 1, then that just tells me that my natural occurrence for my sequence, well, these are all whole numbers. They start at 1, so we go from 1 to 2 to 3 to 4. That just means I'm explicitly writing n. So what could my answer be here? Well, my answer as a result could then be, in this particular case, that we have a -1 to the power of n multiplied by n. All right, so let's see what's going to happen here. If we start at n is equal to 1, well, let's see. n is equal to 1, that's good, because the n is just going to be 1. But then negative 1 to the power of 1 is negative, which means this first term should be negative. And it's not. So what I need to do is I need to manipulate this exponent. I could have n plus 1 as my exponent. Now, whenever I substitute in the value of 1, look at my exponent. That's going to be 2. Negative 1 to the power of 2, it's positive. First term is going to be positive 1. Second term, if n is equal to 2, that's going to be 2 times negative 1 to the power of 3. Negative 1 to the power of 3 is just negative 1. So negative 1 times the initial 2, negative 2. Which means we're able to generate the sequence, which means this is one of our answers. Now, I'm going to tell you this, that sequences or sequence formulas are not unique. All right, and there is no stopping point here, so I'm going to put infinity there. So there is no uniqueness to this. We can find many different formulas that will still satisfy the pattern that we need. All right, they could also start at different indices. All right, at the end of the day, it does not matter. So let's look at the second one again, part B. Let's look at the things that we know that we can extract. Well, number one, once again, it's alternating. All right, so I see that it's alternating. That's great. All right, number two, what else can we see from here? All right, let's see. I see a 4, I see a 1, so there's not much happening there, but then I see a 1/4, 1/16, and 1/64. Notice, as soon as I find out that they're alternating, I automatically cut out the negative values, and I just start looking at the individual numerical portion. So I look at 4, 1, 1/4, 1/16, and 1/64. Typically, the first two don't give me much to go on, but the last three terms actually give me a lot to go on. Because this term, 1/4, kind of looks like 4 to the negative 1, 4 to the power of negative 1. 1/16 kind of looks like 4 to the power of negative 2. 1/64 kind of looks like 4 to the power of negative 3. All right, so it kind of looks like I'm increasing or increasing the power here. So I'm going to go with increasing exponents. All right. So what is then that? What will that then now look like? All right. So let's see. It looks like I have a base of 4, regardless of what I'm looking at. So a base of 4. I'm going to have 4 here. The exponent. All right. I know it's alternating, which means I will have some value that should make this alternate between positive and negative, positive and negative. So let's go ahead and let's account for that positive, and negative as well. Let's make that just negative 4. There we are. Oops. There we are, negative 4. So negative 4 to what power now? Well, let's see. If we're going to start this at n is equal to 1, and we don't have a stopping point, so we're going to go to infinity. At n is equal to 1, we must get 4. All right, so let's see different values that this could possibly produce. All right, so let's see. I'm going to have to do this as, let's say, I can do, let's say n minus 2, and then see how that works out. So if this is n minus 2, all right, doesn't look like it's going to get me what I need. All right, so I don't like that idea anymore. Let's try 2 minus n. Let's see what happens here. All right, so 2 to the power of negative n. If n is equal to 1, let's plug in 1. 1 goes in here, so 2 minus 1. That 2 minus 1 should get me a 1, which means that should get me a 4. But there's a negative in here, and that's my issue. All right, well, that's going to be fine. We can alleviate that issue. We can alleviate that issue if we take out that negative and then put the negative out here as -1, and then -1 to some power. Well, let's go with n plus 1. All right. If we do this, then we can generate exactly what we need. So let me go ahead and clean this up just a little bit more. That way we can see the sequence that I'm generating here. -1 to the power of n plus 1. You can double check this. If n is equal to 1, then that's going to be a positive. N is equal to 2, that's going to be a negative, so on and so forth. And this is 4 to the power of 2 minus n. And again, there are different variations of this formula. This isn't the only formula that works. All right, so just keep that in mind, different variations. But essentially, this is how we're working with sequences. Awesome. So let's start looking at how we're going to start slowly introducing calculus into sequences. All right, so here's going to be the definition that we're going to be looking at. It says that a sequence, a sub n, has the limit L, and we can write that the limits as n approaches infinity for the sequence a sub n is equal to L, or a sub n approaches L as n goes towards infinity. If we can make the terms a sub n as close to L, in other words that limit, as we'd like, by taking n sufficiently large. If the limit of a sub n does exist as n goes towards infinity, then we say that the sequence converges. Otherwise, the sequence diverges. All right, so this is some definitions that we are going to be looking at. We're going to be looking at whether a sequence is convergent or whether it is divergent. So converges, meaning it's convergent. Divergence means that it's going to diverge from a certain value or does not exist, as we're talking about limits. So let's go to Geogebra really quickly, and let's start analyzing some of those different sequences, whether they converge or diverge. All right, so here's one of the sequences that I want to look at first. This sequence is going to be cosine of pi times x. So cosine of pi times x, I want you to then look at this. All right, we go from 1 down to -1, 1, -1, 1, -1. This sequence is alternating, meaning is there one value that as we take these values large enough, so as our n values go large enough, is there one output for this sequence that this sequence is approaching? Well, there isn't. It's either going to be 1 or it's -1. There is no in between. They are not converging, which means at this point in time, cosine of pi times x diverges. This is a non-convergent sequence. Now, let's modify this really quickly then. Let's say I do 2 to the power of, I don't know, let's say -x, just for the fun of it. All right, I'm going to insert a -x here. There we are. So 2 to the power of x multiplied by cosine of x. See if that does it. There we go. All right. Now let's look at this sequence. Well, it starts off almost similar, where we're alternating, but even though we're alternating between positive, negative, positive, negative, positive, negative, look at that. It is still convergent, meaning all of these outputs start getting smaller and smaller and smaller. All of these outputs tend to be outputting towards the number 0. So would this sequence then be convergent as these n values get large? The answer is yes. And this sequence will converge to a value of 0. All right, so now that we get to see the difference between converging and diverging, let's look at one more example here. All right, so let me look at one more example here, and let's look at, let's say I want the square root of, let's say, just x itself. All right, so you're going to see here that as you're outputting these values, as your x values, or in this case, as your n values get large, right, n is equal to 9, well, the output, the a sub n value is going to be 3. And as your n values get larger, so do your a sub n values. In other words, your outputs keep getting larger and larger and larger. There is no one value that these values would essentially plateau or essentially stop at, which means this sequence does not converge. This is a divergent sequence. So we have to be very, very careful the way we talk about sequences, whether they diverge or whether they converge, because, again, we're going to have to be explicit with our definitions and with our constraints to make sure that we observe when they are convergent and when they are divergent. All right, let's go back and let's get a couple more definitions and theorems. That way we can start on a few examples. All right, so here's where we have this definition for the limit, and we have more of a calculus technical definition for it that says a sequence, a sub n, has a limit L, and we're going to write that the limit for a sub n as n goes towards infinity is equal to L if for every epsilon greater than 0, there is a corresponding integer n such that if we take any values greater than that integer, then the difference between the sequence and the limit will be less than that epsilon that we specified. All right, this should remind you of your epsilon delta proofs when we were talking about limits for a particular function back in Calculus 1. All right, now using these two definitions, we're going to talk about the theorem that comes next. And this theorem is going to say if we can have the limit of some function, call it f of x, as x goes to infinity being equal to L, and if we can explicitly define a function for that sequence when a sub n is an integer, then we can take the limit of that sequence as n goes towards infinity, and that's going to be equal to L. Again, making our substitution and making our values, interpreting our functions as regular functions back in Calc 1. All right, so this theorem is going to tie in sequences with the functions that we dealt with back in Calc 1. Now, what we want to look at here when we're talking about the sequence, or when we're talking about sequences, is we need to know some of these limit laws, and these limit laws are going to be very, very applicable to what we saw before when we were looking at limits of functions. Right? If we had the limit of the addition of two functions, then naturally we can take the limit individually of each respective function, take those limits, and then just add the corresponding parts together. All right, so these are the limit laws that we want to observe in this particular section. All right, so keep that in mind. We're going to be using these limit laws as we go through this course, all right, or as we go through the remainder of this course. All right, now I want to talk about a few more items before we move on. I want to talk about a few more definitions and a few more theorems before we move on. All right, so one of the theorems, or one of the theorems that we'd like to use here is a squeeze theorem for sequences. This, again, works very, very similar to the squeeze theorem that you learned back in Calc 1 that said that if you can bound a function by two different functions, one being up top, one being at the bottom of that function, as you start observing their convergence towards a certain value, say as x is approaching a, then if the upper and lower values are converging, so must that middle value of that function. All right, and that's exactly what we're going to be using here, specifically for the squeeze theorem for sequences. We have to make sure that if we can find a bounding for the sequence from below or from above, that as we take those values large enough, they will converge to some limit L. If that happens, then the bounded function between them must also have a limit of L as n goes towards infinity. All right, now another theorem that we're going to look at, and this theorem is, I think, one of the most powerful theorems. It's very underrated. But once you move over to, let's say, Calc 3, this is one of those theorems that actually transfers over quite nice. So if the limit as n goes towards, so here we're going to have if the limit as n goes towards infinity for a sub n, for the absolute value of a sub n is equal to 0, then the limit as n goes towards infinity for a sub n must also be 0 as well. Now, the reason I say this is a really powerful theorem is because I want you to analyze this beginning part of the theorem. The beginning part of the theorem says that if we take the limit of an absolute value of a function that has been explicitly defined for a sequence, and that is 0, then the limit of the actual function itself must be 0. So think about that for these alternating sequences that we can find, right? If we can find that their convergence is happening to be 0 as n goes towards infinity, then naturally that alternating sequence will be nice. Now, we have to be very, very careful here. The converse is not true. Converse for a statement means if you work backwards. If you start here, say if you have the limit as n goes towards infinity for a sub n is equal to 0, will this part be true? And the answer is no, the answer is not going to be true. All right, so this is not an if and only if statement that we look at, it's just an if-then statement. All right, so let's go through a little bit more and let's start identifying a little bit more terminology to see how we're going to be interpreting that terminology or using those terms. All right, so here we are. Now, the three definitions that I want to analyze first is when we have an increasing sequence. So an increasing sequence means that the next term in this sequence is going to be larger than the previous one. All right, so anytime that occurs, we have an increasing sequence. A decreasing sequence, again, once we have a term that the following term is going to be smaller than the previous term, then that's going to cause this to be a decreasing series. And then the very last definition that we have here is when we have a monotonic series. Or, sorry, a monotonic sequence. When we have a monotonic sequence, this is going to mean that our sequence is going to be either increasing or it's going to be decreasing, one or the other. All right, so this is what we want to look at, and this is how we want to identify all of these values, all right, for the sequences. Now, they're going to come out and they're going to play an important role, so we must make sure that we are established with those definitions. Now, the next part. We want to now determine whether the sequence converges or diverges. If it converges, then we must find the limit. And this is going to be for the first part. Part A, we're going to have a sub n, which is going to be 3 times the square root of n divided by the square root of n plus 2. All right. So again, we're going to see whether the sequence converges or diverges. Now, what I'm going to do here is I'm actually going to use this theorem right here. All right, that says if I can establish that the limit as x goes towards infinity for some function f of x is equal to L, then when I make my substitutions for that explicit function in my sequence, then that limit should still hold. All right, so what it is that I'm doing here is I'm going to use f of x as 3 times the square root of x divided by the square root of x plus 2. So to see whether this converges or diverges, now I'm going to have to look at the limit as x goes towards infinity, and that's going to be for this function here. This is going to be for 3 times the square root of x divided by the square root of x plus 2. Now, if you remember back from Calc 1, the way we do this is we multiply both numerator and denominator by the variable with the highest exponent in the denominator. All right, when we do this, we can divide out by it. My apologies. We can divide out by that. There we are. So when we divide out by this, we now get the limit as x goes towards infinity, and this is going to be for 3 divided by 1 plus 2 divided by the square root of x. Now, as x tends towards infinity, this little piece here, 2 divided by the square root of x, well, this is going to go towards 0, which means we're going to get a value of 3. And this is our limit for that function. So the one thing that we found was that the limit as x tends to infinity for f of x is equal to L. So when we make our substitution and when we now use, well, let's say f of n is equal to a sub n, then that means the function that I was initially looking at now is going to be equal to 3. So what we have here is that the limit as n goes to infinity for 3 square root of n divided by the square root of n plus 2, this must equal to L, which was the original limit that we found, which is 3. So, in this case, the sequence converges. Alright, so the sequence does converge, and we found that converging number. It actually converges to the number 3. Alright, that's pretty good. Let's go ahead and check on Geogebra just to make sure that this is in fact the limit that we're looking at. Alright, here I am on Geogebra, and I'm going to make sure I have exactly what I need. So I want in my numerator to be 3 times the square root of, in this case, let me say x. Here we go, x. There we are. And then I'm going to divide out. So let's divide out by my numerator. And my numerator is that square root of x. Oops, excuse me there. There we go. That denominator is that square root of x plus 2, so I'm just going to add up plus 2 in here. There we are. And I'm going to hit enter really quick just to make sure. Alright, my little box there tells me that I have the exact same sequence. There we are. Now, looking at my sequence here, yeah, it definitely does look like it might actually start converging to 3. Now, as x gets very, very large, notice that these numbers are, again, between 2 and 4, which 3 is right smack in the middle. So it is actually converging to 3, but it's converging to 3 at a very, very slow rate. And that's okay, as long as it's converging. Awesome. So we now get to see the process here as we start exploring these ideas. Great. Let's go back. Alright, so here we go, part B now. For part B, I want to look at this sequence here. Let's call this B sub n. And we're going to have b sub n be the nth root of, let's say, 2 to the power of 1 plus 3n, as such. There we are. And again, we now have to figure out what's going on here. So one of the first things that I always like to do is, again, let's interpret it as a function. So I want to use f of x as the nth root, or in this case the x root of 2 to the power of 1 plus 3x. Now, looking at this and trying to take a limit, yeah, it's going to be really tough. We're going to have to use some items maybe from early Calc 2, where we were using these transcendental functions to figure out what is the limit of this exponential function, logarithmic function, anything like that. Alright, so before I do that, I think I want to use algebra here. So I have the nth root. Alright, so actually, let's write it this way. It'll make things a little bit easier if we do it this way. There we are. Oops, excuse me. Gosh, I'm used to writing n, and in this case I want to write x. There we are. So as I start looking at this, let's look at my radicand. My radicand here, now noticing that my exponents are being added to one another, that's going to tell me that my bases are really just multiplying one another. And I have this value here to the power of 1 over x. Now, using my algebraic properties, I'm going to distribute this exponent, which is going to get me 2 to the power of 1 over x multiplied by 2 to the power of 3x multiplied to the power of 1 over x. All right, because again, I distributed that exponent there. All right, the only reason we can do that is because the bases are being multiplied. So once I have this taking place, now I can see that this first term just becomes 2 to the power of 1 over x. And this second term, notice the x's are going to cancel, and we're just going to get 2 to the power of 3. This means that I'm looking at 8 times 2 to the power of 1 over x. That is not too bad, because now I can then say, well, let's look at the limit as x goes towards infinity for this function as such. Well, that's just going to be the limit as x goes towards infinity for 8 times 2 to the power of 1 over x. Now, using your limit laws that we discussed back over here, we can say, hey, we have some sort of constant, so we're going to have some sort of constant multiplied by the sequence values, so that means we can factor out the constant through that limit. So as I'm looking at this limit is going to be 8 times the limit as x towards infinity, and this is going to be just 2 to the power of 1 over x. So let's keep going. As x gets large enough, so let's look at this numerator. X is going to get large enough. This means that this numerator, this denominator is going to get very, very large. That means this exponent is just going to tend to 0. All right. Now, what does that look like? Well, I'm just going to say recall that the limit as x goes towards infinity for 1 over x, this is equal to 0, which means this numerator, that's exactly what's going to happen. So what's going to take place here is that we're going to have 8 times 2 to the power of 0 once that limit is allowed to go towards infinity, which just means that we get a value of 8. So how do we then analyze this? Well, we can then analyze and say, hey, you know what? We found a function, call this f sub n, and f sub n is going to be equal to the sequence that was defined. So we're then going to be able to have the limit as n goes towards infinity for the nth root of 2 to the power of 1 plus 3n. Whoa, that 3n does not look well. There we go. 2 to the power of 1 plus 3n, this is going to be equal to the limit that we found, which is 8. Thus, the sequence converges. There we are. So again, we must always go through those values, and we must always go through these arguments. Will the sequence converge? If it does, again, you have to go through the arguments and show me that it does converge. All right, try to use all of the tools at your disposal that we were talking about. All right, so let's talk about a function or a sequence being bounded. All right, this is going to be one of those other important topics that we need. All right, so here are the 3 definitions that we're going to need. If a sequence is bounded above, all right, if it's bounded above, then there's going to exist a number, call it m, that is going to be a bound for that sequence, meaning it's never going to exceed that specific number. So in the case of the y values, you're kind of thinking about this as your outputs. If your outputs are bounded by some value, some limit that they never attain or that they can't attain, it means that that sequence is then bounded. Similarly, if we are bounded from below, that means that we attain, or we try to attain, a number that is the lowest number within that sequence. It might attain it, it might not. All right, so the next one is going to say that if it's bounded above and below, then what we're going to have is a bounded sequence. All right, and we're talking about these definitions because we're going to be looking at this one theorem, or I should say we're going to be using this one theorem. This one theorem that we have here is the Monotonic Sequence theorem. And now this theorem is actually really nice. All right, so let's actually go a little bit more. There we go. This is going to be your Monotonic Sequence theorem. Now, this monotonic sequence theorem, what this says is that every bounded monotonic sequence is convergent. Now, this is huge. All right, this is huge. The reason why this is huge is because this now uses the whole idea, or the whole concept, of a sequence being monotonic. This now says, okay, you're going to have this monotonic sequence, which it's either going to be increasing or decreasing, whatever it may be, and if that sequence is then bounded, so if we can bound a sequence, then it must be convergent. All right, so that is unique there. So as long as we can identify, hey, we have a bounded sequence and it's monotonic, hey, you're going to be convergent. This is going to be one of those huge items, one of those huge tools that we're going to want to keep in our toolbox as we proceed through the semester. All right, so keep that in mind, and this now will wrap up section 11.1, where we're talking about sequences. All right, so I hope you all enjoyed this lesson, and I hope you all stay tuned for the next part where we're going to be talking about series.